Greetings, Mathemopolis, once again. Now, today we're going to be starting a series on this channel called Applications of Calculus. This is taking calculus and trying to apply it to a more physical space, something that could actually be applied to something. And so we're going to start very basic so we can start to build off of this basic concept. So we're going to be doing how to find the area between two curves. So let's say we have a function, let's just call it Gilbert. So how would we find the area under the function Gilbert? Well, of course, we would just take the antiderivative of that from the bounds that it gives us from, let's just say 0 to, let's call that red one a. So we would take the antiderivative of that, and whatever number value we would get from plugging that into a calculator or doing the math by hand would be the area underneath the function Gilbert. That should have been in review. That was just simply what an antiderivative was. An antiderivative is the area underneath a curve. But now if we add another curve and they overlap each other at some point, we want to find the area between those two curves. So to do this, we could think about it as kind of breaking up the two curves. So on one graph we would have Gilbert, the function Gilbert, and then on the other graph we would have y equals square root of x. And then you would take their antiderivatives, find their areas, and then subtract them. And when you're doing this step, you have to be very careful about what function you're actually subtracting. So the rule of thumb generally goes, you should do it top minus bottom. So whatever function is the topmost function, in this case it would be Gilbert, would come first because it's the larger function. And then you'd be subtracting the smaller function, which is the bottommost function. So now let's try an example together. So we have y equals x squared plus 2 and y equals negative x, and we want to find the area of these two functions, between these two functions, from x equals 0 to x equals 1. We're only worried about that space. Let's very quickly look at our graph and think about which one of these functions would be the top or the bottom. So looking at it, you can see that the blue function y equals x squared plus 2 is the top function, is literally above the orange one. So we're going to be subtracting the orange function's antiderivative from the blue function's antiderivative. It's Mathemopolis time. Now, before I do this, I would recommend that you give this problem a shot before I go ahead and answer it. So I'll give you a couple seconds to do that. That was sufficient time. So we're going to take the antiderivative of x squared plus 2 minus negative x. We're going to combine them first. So we get x squared plus x plus 2. And now we're going to take the antiderivative of that. So we get x to the third power divided by 3 plus x squared divided by 2 plus 2x. We're going to evaluate it from 0 to 1. So evaluating, we end up getting, plugging in 1, 1/3 plus 1/2 plus 2. And then we can ignore the 0. We don't have to worry about the 0. So, because it's just going to be minus 0. So, don't even do it. So, adding that up, don't you dare touch that calculator. We end up getting 17 over 6. And if you did not get that answer, you should not need a mathematical equation to tell you there is no hope. Give up now. Now, let's look at a different example. Now, with these two curves given to us, x equals 3 minus y squared and x equals y plus 1, you could do it the way that we just did it, but you would have to do that in two separate steps. So let's try to avoid that, and let's just take the antiderivative of it with respect to y. So we're going to have to do some different steps, but it's very similar. So the first thing that we should do is take these two equations and set them equal to each other and solve for y. So this way we can find the y values at which they intersect each other, and we're going to use those as the upper and lower bounds when we take the antiderivative. So when setting this up, the order that we subtract our functions is a little bit different. We're not going to do top minus bottom. If you were to do top minus bottom, you'd have to do it in 2 steps. That's a little more difficult. So we're going to do right minus left. The rightmost function, the blue function, x equals 3 minus y squared, minus the left function, the orange function, x equals y plus 1. Let's combine what's in those parentheses. So we should get 2 minus y squared. Let's take the antiderivative of that, and we should get 2y minus y squared over 2 minus y to the third over 3. We evaluate it from 1 to negative 2. So we should write out this work because this is a little bit more complicated than the last one. Plugging in 1, we should get 7 over 6, and plugging in negative 2, and subtracting it from that 7 over 6, we should end up getting a 9 halves. Let's just try one more problem. This is a two-step problem. So we're going to try to find the area bound by the graphs y equals 3x to the third minus x squared minus 10x, and y equals negative x squared plus 2x. As I mentioned before, this is a two-step problem, meaning that we're going to have to switch which one of these functions is the top and which one is the bottom. So just like the last problem, we are going to set the two equations equal to each other and solve for x in this case. And those are going to give us the intersection points, and those are going to be our bounds for our two intervals to integrate. So what this really means is from the interval negative 2 to 0, the blue function is on top, while the orange function is on bottom. And then when you get to 0, from 0 to 2, the orange function is on top, and the blue function is on bottom. So we're just going to integrate it in two parts and add them together, and that will be the area underneath those two curves. Thank you so much for watching this video. In the next video, we will be talking about the disk method, which builds off of this topic that we covered today. If you would be so kind to subscribe, leave a like, hit the bell notification icon so you don't miss my next episode of Applications of Calculus.